So Ms. Stone is gonna record this, and we're just gonna go through this whole silly worksheet together as a crew, and it's gonna be what it's gonna be. So here we go. So we're gonna look at polarity. The first question on this worksheet asks how the comic book defines a polar molecule. So if you think about, sometimes people will talk about things being polar opposites or whatever. So this is how we're using this in chemistry. And I'm gonna close the chat so that it's not in the way. So right up here at the top, it says that we don't have to go to the ends of the earth to find polar molecules. They're all over the place. A polar molecule, ding, 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 here it is just a molecule with a difference in electrical charges between the two ends. So this is really just a matter of copying that down. So the comic book says a polar molecule, it's defined as, it's a molecule with a difference in electrical charges between the two ends. Probably not the word the. That's it. It's just a difference in charges between two ends. And when you have a difference in charges, it ends up so that the positive side of one molecule will attract to the negative side of another molecule. So that really is why water does all the things it does, is because it's a polar molecule. Then we need to think about electronegativity, and electronegativity is a concept that we talked about. I don't know if you guys remember when we looked at all of those graphs of the different periodic trends and tried to relate them to a periodic table. The first one you did was electronegativity, and we saw that the electronegativity increased as you went across the period. And then we did ionization energy, which was the energy required to steal an electron. And the energy to steal an electron increased as we went across. And then I think the last one that we did was electron affinity, which was how much energy was released when an element added an electron to itself. And we saw that also increased as we go across, because as you go across the periodic table, the atoms want electrons more and more and more and more. Because like if you're right here, if you're fluorine, you only need one more electron to have an electrical outer shell that looks like neon, that's completely full. And that's like very energetically favorable. So that's what is happening with all of these things. So electronegativity, from the first 2 pages of the comic book, if you want to, why don't we take a few minutes? I'm not going to make you all do popcorn reading, because I get texts at least twice a week from my daughter, like kind of freaking out because they're popcorn reading in class, and it makes her really nervous because she doesn't want someone to call on her. So I'm not going to do that, but I would like us to go through these first couple of pages together. So if there are any volunteers who would like to read the first little section, that's great. If not, I will bore you with my own voice. Travis is like, no, please no. Totally fair. Okay, I'll go ahead and read this. I know it's kind of lame, but I'm not going to make you all read out loud because I think it's unpleasant. So, polarity in molecules is caused by a difference in electronegativity between atoms. Electronegativity describes the ability of an atom to attract bonding electrons towards itself. So that is what electronegativity is. So if you look at the little drawing, you can see that you've got hydrogen has a plus next to it and the chlorine has a negative next to it. And then you've got this big chlorine polar bear licking the ice cream cones, and the penguin's like, hey, where's my ice cream? So chlorine is more electronegative than hydrogen. So the bonded pair of electrons right here, spend more time near the chlorine, because the chlorine is if you think about the nucleus of a chlorine atom, it has 17 protons, and the hydrogen only has 1 proton. So these 2 electrons right here are going to be way more attracted to the chlorine because the chlorine has 17 positive charges to attract those 2 negative charges, while the hydrogen is really just 1 proton. So it's not nearly as attractive. It's like a 17 plus charge compared to a 1 plus charge. It's pretty evident that you're going to be more attracted to the 17 positive charges. Electronegativity values tend to increase as you move northeast on the periodic table and decrease as you move southwest. So if you look at this periodic table, you've got little teeny tiny penguins. So these are not very good at holding on to electrons. Not very good at tug of war. And then you've got this big, huge polar bear penguin, or this big, huge polar bear who's very, very strong and very good at tug of war. And I think of tug of war as what they're doing to the electrons that are bonded. So if you think about this, you've got this chlorine, which on the periodic table is like right here, fighting with the hydrogen. And this is definitely going to be a stronger competitor right down here at the tug of war than this tiny little penguin. That's kind of how it works in my brain. And that is what you're getting today. So when the 2 atoms with different electronegativity bonds value, the bonding electrons spend more time around the more electronegative atom, creating a partial negative charge on that atom. The other atom then has a partial positive charge, and the bond is what we call polar. Because remember, polar means that there's a difference in electrical charges between ends of an atom. So you've got this poor penguin saying, hey, polarity is not fair. And the chlorine is saying, oh, try to be positive. It's super cheesy, and I would apologize, but I'm not going to. When the atoms with equal electronegativity values bond, they form nonpolar bonds because the electron attracting strength between each of the atoms is the same. So if 2 twins are arm wrestling, it's going to be a pretty fair fight unless one of them is, super into the gym and the other one's not. Same thing here. So you can have 2 big, strong things fighting, and it's going to be an equal fight, or you can have 2 weaker things fighting, and that's also going to be an equal fight. So it really depends on how hard they pull on those electrons in the bond. If the electronegativities of 2 bonded atoms are different, then their bond is going to be polarized, maybe a little. So imagine a big, huge polar bear arm wrestling a little tiny penguin, and the penguin is getting its little penguin tushy kicked. Sometimes it's pretty significant. So after reading through those first 2 pages, close your eyes. I'm going to scroll up, and it's nauseating. Ooh, look at that. I did it fast enough that it just clicked. That's great. That's fast. That's good. Okay, so electronegativity as we understand it after reading the first couple of pages of the comic book. Anybody have thoughts? What did we just talk about? Yeah, so we talked about hydrogen being less electronegative. Wow, you got to write the word, Annie. Less electronegative than chlorine. And why is that? What is chlorine better at doing than hydrogen is better at? What'd you have? You're not wrong. What'd you have written?
Oh, no.
Oh, okay.
Wasn't it, they have the ability to attract and have more efficiently?
Yeah. So the electronegative elements are better at attracting electrons to themselves, right? So electronegativity is, more electronegative atoms. Electronegativity is an atom's bond, or an atom's ability to attract electrons to itself, bonded electrons. So if you have something that, like the chlorine, was really good at pulling on those electrons to itself because it has more protons in its nucleus, so it's stronger. In my mind, electronegativity is a tug of war. Or they were using the analogy of arm wrestling. Okay. So then they want us to look at the picture at the bottom of page 1 and explain how the iceberg, the penguins, and the polar bears represent trends in electronegativity. So I'm going to try to do this fast. It didn't work. You have to watch it. All right, so it wants to know how this is representing the trends in electronegativity. So what do you notice about the different critters on either side of the periodic table down here? Oh, first of all, this whole situation here kind of looks like a periodic table. So the iceberg is shaped like a periodic table. So that's one thing. Did you see that? Yeah. Yep, the shape is meant to be a periodic table. And then if you look at this, we've got these big old polar bears on the right-hand side of the periodic table. So lots of electronegativity on the right-hand side of the periodic table. And these little teeny tiny penguins that get smaller as you go down, and the stuff gets bigger as you go across and bigger as you go up. If you look, this polar bear is smaller than this polar bear. So it's showing you that the electronegativity decreases as you go down and increases as you go across and increases as you go up. So close your eyes. I'm going back up to the top. We're going to make some kind of a better at going up. All right. So the iceberg is shaped like the periodic table. And the penguins represent the low electronegativity. And the polar bears represent the high electronegativity. And we saw that we have big penguins at the top of the periodic table and smaller penguins at the bottom. Wow, that's not really a word right there. And you could substitute out the word polar bear for penguin. So we found bigger critters at the top and smaller critters at the bottom. I'm not going to try to write that because it will be hard to read. So we've got our most electronegative atoms are at the top of the periodic table, and the least electronegative atoms are at the bottom of the periodic table. And it has to do with how close the bonded electrons are to the nucleus. So if you look at the periodic table here, if we've got stuff up here at the top of the periodic table, the bonded electrons are closer to the nucleus. Down here at the bottom of the periodic table, these things are a lot further away from the nucleus than they are than the ones at the top. The ones at the top bond really close to the nucleus. The ones at the bottom bond like way out there. It's like if you add kids to a class and they're like way the heck out there, and it's harder to pay attention because the light in the room is lovely and you just want to stare out the window instead of paying attention to the crazy teacher at the front of the room. That kind of a thing. The atoms are less good at pulling electrons to themselves when the atoms get bigger and bigger because the electrons are added further and further away. So the next question asks what the artist is trying to represent, where there are two polar bears arm wrestling together. and two penguins arm wrestling together. So what is that meant to signify when we've got the whole arm wrestling situation going on? What? Yeah, it's the equal attraction. If you look, if you've got two polar bears and they're arm wrestling there, you've got an equal, it's like arm wrestling with your twin, right? When you're both doing the same workout regimen. So they're showing two atoms with very similar, wow, you can't, there we go. Very similar electronegativity. So they have an equal pull on the electrons. So we've got an even match. There's nobody's hogging anything. And when that happens, you're going to end up with a non-polar, you're going to have a non-polar bond because the attraction for the electrons is equal. And this difference in electronegativities and polarity ends up being really important as we look at the rest of the stuff over these next couple weeks, looking at how water interacts with other water molecules, how water interacts with salt ions, or how it interacts with oil molecules. It's all going to depend on the electronegativity. I think this is one of the most important pieces in all of chemistry, is understanding electronegativity and how the polarity of different molecules affect their interactions with other molecules. So next, it's asking me what 3 types of bonds are represented on page 3 of the comic book, and what happens to the bonding electrons in each type of bond. So close your eyes. I'm going to flip down to page 3. Eventually. Okay, so we've got 3 different types of bonds and what is happening to the electrons. So if we look at, this says, because the elements have such varying electronegativities and can bond in many different combinations, there really is a continuum. So a continuum is something that like is sort of a shaded situation, like that. Right? It starts one way and then changes gradually to something else, sort of like what we're doing with the pandemic, right? Like as more and more folks get vaccinated and we're able to sort of slowly reach a point where we're going to be able, hopefully, to resume something more similar to real like life, like we're a little more used to. That's kind of the same idea with the polarity, that depending, it's not like a switch that's flipped and something automatically happens, but it slowly, there's a progression of different polarities. So you can break the continuum down into 3 basic categories. You've got the non-polar covalent, where you're fighting and the battle is even because everybody has the same electronegativity. So those are going to be like in identical atoms, like hydrogen, H2, N2, O2, or Cl2, where you've got exactly the same electronegativity. So if you look at this one, they're both equally getting their tongues on that ice cream. They're both sharing the electrons the same. And super nerdy, if you think about the Lewis dot diagrams that we drew the other day, if each of these represents one little electron, they're sharing 4 scoops of ice cream. So that's a double bond, folks. I'm telling you, chemistry has all kinds of little stupid details, and they all matter and they all mean something. Almost everything on this comic book has another meaning to it. These cute little penguins over here, they're sharing 2 electrons because remember, hydrogen only needs 2 electrons to fill its outer shell. One thing that they could have done, that if they were really going hard on this analogy, is they could have put ice cream cones out here on the oxygen, because remember, oxygen always has 2 lone pairs. So that would give it its 8 if we were going real hard with the analogy, but it's okay. Polar covalent happens when you have two atoms sharing bonded electrons that are somewhat unequal, and the electrons are more attracted to one atom than to the other. This would be, I guess I can read it right off of here, can't I? So this would be like between carbon and oxygen, or between hydrogen and fluorine, or between hydrogen and oxygen, as we will see. So this is where you have something stronger. You can see the polar bear is getting its tongue on the ice cream or on the electrons. It's pulling on those electrons harder. And the penguin is like, I'm gonna just let you have, I'm not gonna totally give you my ice cream. I'm still gonna hold on to it, but you can definitely have more of that ice cream. It's fine. I'll just take a bite. It's cool. We're good. So that's what's happening in a nonpolar bond. And then in ionic, you've got huge differences, and it's basically where the penguin just says, dude, take it. You can just have my ice cream. I'm good. I'll bounce. It's no big deal. So big differences in electronegativity results in the winner takes all situation of ionic bonding. So the more electronegative atom fully steals the electron of the not very electronegative atom. And then they end up with opposite charges, and then they need to hang out together to balance each other's charges. So close your eyes. So we have nonpolar covalent, and we have equal sharing of electrons there. And this is going to be important. We're going to spend a lot of time over the next week or two looking at the difference between nonpolar, polar covalent, and then ionic bonds. So in a polar covalent, you have unequal sharing. So somebody's hogging the electrons. And then in ionic, you have a full-on stealing of electrons. So the difference in electronegativity is so big that the electrons just get stolen. It's so unequal that the electrons are transferred. And you end up with a positive and a negative charge, and they have to spend time, they have to stay together because now one's positive and one is negative, and they need each other to, because none, it's not energetically favorable to support a charge when you're just a single particle. It's a lot better to spread that charge out and balance it with something else. Okay, halfway done. Why were there 4 scoops of ice cream in O2? We talked about this. Oxygen, remember, has 6 valence electrons. So if we draw a Lewis dot diagram for oxygen, we've got like this, 0, 2, 3, 4, 5, 6. And we see that we can form a bond here and a bond here. So oxygen ends up forming a double bond. And remember, I drew those ice cream scoops out on the side of the polar bear. So it's because there's a double bond, and they're sharing 4 electrons. Whoa, they're sharing 4 electrons. And then there are 6 ice cream scoops in N2, and I'm not gonna scroll down there. I'm just gonna and show you 6 ice cream scoops right here. And so if you remember from our Lewis dot diagrams with nitrogen N2, we know that they have a triple bond. You've got nitrogen, and it has 3 bonds to another nitrogen, and they each have a lone pair. So if you look at this nitrogen, it has 2 electrons that are by itself and 6 electrons that are in a bond. So it has 8 electrons on both of the different nitrogens have that same electrical structure. So they're complete. So what do you think is happening to the penguin and the CO2 molecule in the picture on page 4? Okay, close your eyes. Maybe it doesn't make you nauseous. It makes me nauseous. when it scrolls like this. There it goes. Okay, so polar bonds between atoms create dipoles, and the word dipole, because we already did that one. Yeah, okay. A dipole can refer to the polarity of an individual polar bond between atoms, or it can refer to an overall dipole in the molecule, and that depends on having polar bonds and the shape of the molecule. So I just said that. Confusing. Here are some examples. So N2 isn't a dipole, and it doesn't have any dipoles. So the nitrogens both have the same pull on the electrons. You can see the tongues are equally on the ice cream. It's non-polar, no polar bonds, and no polar. The molecule itself is non-polar. Hydrochloric acid has a dipole in between the bond because the hydrogen is weak and the chlorine is really strong, and it has it's a polar molecule because of the shape of the molecule. So if you look at the shape of this, you've got your electrons being pulled towards the chlorine, and the hydrogen ends up positive. So we'll draw this little symbol to show the electrons are going this way over here, and then that leaves the other side kind of positive. So we cross it to denote like, hey, this side's positive, this side ends up kind of negative. If you look at carbon dioxide, give it a second. Come on, computer. There you go. Carbon dioxide has two dipoles. So if you look here, the carbon is not very electronegative. So its electrons get hogged towards the oxygen, leaving the carbon positive. And then there's another one that balances. So it gets pulled off to the other side, leaving the carbon dioxide in the middle positive. So this poor penguin is being pulled both ways, and it ends up, but because it's balanced, the molecule itself is not polar. So you can have two polar bonds in a molecule, but as long as they're being balanced, the molecule itself isn't polar. Now, if I had carbon monoxide where one of these didn't exist and the electrons were only going this direction, carbon monoxide would be a positive, would be polar. But that's not what we have. We have carbon dioxide. It's being pulled equally, and so the molecule itself is not a polar bond. Water also has two dipoles, but because water is a bent-shaped molecule, and I kind of hinted at this when we were drawing Lewis dot diagrams, but because water is bent, it ends up, there we go, it ends up being a polar molecule because these two, you've got an oxygen bonded to a hydrogen hogging on the electrons. The oxygen hogs the electrons, the hydrogen's positive. You've got an oxygen hogging electrons from a hydrogen. So this ends up partially positive down here and partially negative up here. So you end up partially positive down here in the hydrogens and partially negative up here at the oxygen. And that right there is what we're going to talk about for the next like week and a half. So you've got your oxygen hogging electrons, and because it's not balanced, there's nothing balancing the top of that polar bear's head. So the electrons end up hanging out by the polar bear more, by the oxygen more, and it ends up being positive down by the hydrogens. Okay, that's huge, major. So the polarity of molecules affects all kinds of things with how they dissolve, how they attract to one another, their melting points, how they smell. And I'm not going to read that because it's super cheesy, but it's accurate. Polar bears and penguins do not live at the same pole. So there's a little biology for you. All right, close your eyes. Let's finish this up. Okay, so the CO2 guy is having his arms yanked. CO2, arms being yanked, but it's balanced. So it's nonpolar because the dipoles balance each other. So you got carbon and it's being pulled this way and it's being pulled this way, but it's balanced. There's no net pull. The pulls balance each other out. Three things that the picture of carbon dioxide illustrated about the molecule. What's one thing that we see that this illustrates about the penguin? It number 9, yeah, number 9. What are some things that you see? What's representing the carbon atom? Which critter? Yeah, the penguin. So we have the penguin is carbon. So that means that it's low electronegativity. It's not very good at pulling on electrons in a bond. And your oxygens are polar bears. So high electronegativity. It is such a long word. I'm with you, Travis. And then look at how many, what are these called? Ice cream scoops. How many ice cream scoops are they sharing in each spot? 4. Yep. So they're sharing 4 electrons because there are double bonds. So 4 ice cream scoops because of the double bonds. All right, and we just talked about what's happening with water. The oxygen hogs the electrons, and it's an unbalanced molecule. So you end up with the hydrogen, oxygen, that, and the electrons get pulled towards the oxygen, the hydrogen's positive, electrons pulled towards the oxygen, hydrogen's positive, and overall that gives us a net dipole. So this ends up being a polar molecule where you've got the negative up here by the oxygen and then the positive out here with the hydrogens. The crossed arrow, we talked about this, it's a positive charge because the electrons are over here. So it shows you the direction that the electrons are going in the bond, where they're being more attracted. And then 2 definitions of dipole given in the comic book. I don't know this one off the top of my head. It refers to the polarity of an individual polar bond between atoms and the net polarity of the polar molecule. And yeah, okay, that makes sense. So the answer is that you can have a dipole. A dipole can refer to just the polarity of the bond. So oxygen and hydrogen, there's a polarity between the oxygen hogs on the electrons, or the overall dipole of a molecule. Like with the water that I drew right here, if you look at this one, you've got you can't even see what that is anymore, but you basically, if you have a bent shaped molecule, if you have a molecule that's not symmetrical, it'll end up having a polar part. It'll be negative in one place and positive in another place if there's a polar bond. So, so electronegativity has to do everything with polarity. So the strength of the attraction to electrons is what dictates where there's a positive and where there's a negative. And then the shape of the molecule will mean that the whole molecule is polar. So electronegativity has everything to do with polarity because the location of electrons in a bond dictates the charge in places on an atom or in places in a molecule. So if you've got electrons in one place, you're going to have a partial negative charge and a partial positive charge on the opposite side. And this little thing means partial. It's a lowercase delta in Greek because in science we run out of variables and we end up going to the Greek alphabet. So you know you're a nerd when you can drive down like sorority row and you're not in a sorority or a frat, but you know what all the symbols mean because of physics and math class. That's a true nerd. Were there nerdy frats and stuff at OSU, Morgan? Was there one that was full of super nerds?
Probably.
We think there probably are.
I mean,
There's got to
it's
be.
an engineering school.
Yeah, exactly.
For sure there is.
Partial. Okay. I'm not going to make you do the last one. If you want to do it, you can. Thank you for listening to this. I know it was long and I know that we're sleepy and it's Friday, but